Hello everyone, welcome to the Metadata Perspective channel. In our today's video, we are going to be learning how I carried out this project to analyze the cancer patient dataset using Python. This dataset was gotten from Cargo, and as usual, I'll be dropping the link in the description section. So in case you're interested in coding along with me, you can go ahead and download this dataset. This video is a continuation of our previous video, so if you've not watched the previous video, which will be popping up on your screen right now, I would advise you to pause this first and go ahead and watch that. Now with that being said, let's go straight into analyzing our data for today. So the next thing we'll be doing is to identify skewness and outliers. So how skewed is these columns, data values. So to check for skewness, you can just simply call on the .skew method. You can see that when you are analyzing a data set with Python, it's actually easy and straightforward. You just have to know the method, the functions, the attributes you want to call. Once you know it, it's always very easy and straightforward. You don't need to do too much. So calling on the .skew method, we are going to be getting the skewness of the H column, and with this we can see that the skewness of our H column is 0.003. and to make this easier, I just created an if else block to check if this value is greater than 0. It's going to be printing out a statement telling me the type of distribution of that particular column. So let's say, for example, the skewness value of the H column is 0.03, and I'll be checking if this value is greater than 0. If it's greater than 0, it's going to print it's right skewed or it's positively skewed, and the tail is longer on the right. While if the skew value is lesser than 0, it's going to say it is left skewed or negatively skewed, and the tail is longer on the right. Then if this value is equals to 0, meaning it is not greater than 0, it's not lesser than 0, it's going to return and tell me we have a normal distribution. So that's an easy way for you to get how skewed your data column is. Now remember, we're not just checking for skewness, we also want to get the outliers. Okay, so for this I only checked for the skewness of age. So if you're coding along with me, you can replace this with your height column or your weight column to also get the skewness of those columns. So the next thing I'll be doing is to look at outliers in our data set. So do I have any outliers, any extreme high age values or extremely low age values? So those are outliers, right? So to get outliers is Q1 minus 1.5 times IQ arrow, which is your lower bound, while your upper bound is Q3 plus 1.5 times IQ arrow. So how do you get your Q1? Your Q1 is your quantile, your first quantile. So you can just call on the dot quantile and pass it your 0.25, and you'll be getting your Q1 on that column. Your Q3 is your 75th quantile, right? So you can just do same process, passing 0.75, you'll be getting your Q3 values, and you can, to get your IQ arrow, you'll be subtracting Q1 from Q3. So with this, we've been able to define our bands for our outliers. Q1, which you've gotten using dot quantile, 0.25 minus 1.5 times your IQ arrow, which is Q3 minus Q1. So you set your lower band and your upper band, and with this we can filter out our outliers. So you see, when I filtered out these outliers, it returned an empty data frame stating that we don't have any outlier for the age column. Remember that when we check our age column, the lowest age, let me go and scroll this a bit up, the lowest age value was 18 years, and this value is not extremely low, right? While the highest was 89. So you can see these values are within range. So let me take this down. So there was no outliers for our age column. So the next column I looked at is the weight column to check for outliers. Using same process, finding your first quantile, your third quantile, subtract your first quantile from your third quantile, get your IQR, and set your lower band and your upper band. And you can see with this we're able to filter out our outliers, and our unique outliers values was this 27, 18. So we have weights as low as 27 kg, 18 kg, 24, 28, 29, and this is probably real outliers, because remember that the lowest age we had was 18 years. And is it possible for somebody to be weighing 27 kg? Okay, so we would have to do more data analysis, or in this situation you would have to ask your data collector where your data is being collected from. Are these mistake, or are these the actual weight of these patients? But with the thing with medical data is that it's not usually very easy for you to drop outliers, because why I said so is you have to put in a lot into consideration. Remember, these patients are suffering from cancer, and with cancer treatment you tend to lose weight, right? So that's why I said in a real life situation we would have to go back to the data collector and ask and get proper findings and check if these are the actual weight values, because there might be a situation where this patient has reduced or lost weight to, I don't know if it's possible to this extent. I don't know if it's possible or not. Okay, so but I'm just trying to give you an understanding why in medical data you don't just go ahead to drop rows of data when analyzing. You need to ensure that you've done proper findings and ensure that these data are actually outliers before you go ahead and drop them. The next thing I did was to create a visualization of this column so that we can get our outliers. Or what's the best chart you can use to visualize outliers if not box plot? For box plot, you remember that the dot points represent outliers, so any values outside these whiskers are outliers, right? So you can see we have a whole lot of low values and values that are extremely high. Now we can now go ahead and visualize relationships. So let's go back to our exploratory data analysis step. So we'll be visualizing data relationships. So let's look at some columns and see how they relate to one another. So the first visualization we'll be looking at is a scatter plot. Scatter plot is used to show relationship between two numeric columns, right? So we'll be looking at the weight column and the height column, and we're trying to see if there's any relationship between these two columns. Is there any correlationship? Does increase in weight affect height? So that's what we're trying to look at. So with these points you can see that there is no relationship. If there was a relationship, you'll be seeing probably a straight line where most of these data points will be clustered along that straight line, right? But you can see that these data points are spread out everywhere. So the next thing I did was also to look at the distribution of cancer type for each gender. Remember, we have our gender, 3 genders: female, male, and others. Now we're looking at the various cancer type. There are some cancers that are specific to particular genders, right? So we are going to imagine that for some genders they are going to have more occurrence of that particular cancer for those genders, right? So let's see if that is actually true with this data frame. So for cancer of the liver, you can see that we have more female patients. For leukemia, we had more male patients. For lung cancer, male and female are almost equivalent. For cancer of the pancreas, we had more female patients. For breast cancer, we had more female patients. For ovarian cancer, we have more male patients. You can see there's something fishy here, right? Because male do not have ovaries. So how are we having more male having ovarian cancer? So this is another situation where we would have to interrogate this data, the data collector, and ask, there's something fishy. was there any mistake when you were collecting this data? Okay, so you can see why exploratory data analysis is very important when it comes to analyzing data. It's going to give you findings, it's going to give you insights about your data sets. So for prostate cancer, you can even see for prostate cancer we are having almost equivalent values of females to male. And do female have prostate? Okay, so why have females having prostate cancer? So these are questions we need to ask our data collector. So the next thing we'll be looking at is distribution of cancer stage. So we have 4 stages of cancer here: stage 1, stage 2, stage 3, and stage 4. So we'll be looking at each stage. Where do we have more patients? Which stage have most of the patients been to? So you can see we have more patients in stage 2 and in stage 3. Okay, we have fewer patients in stage 4. So for the cause of death, we had more patients that had complications as a result of cancer, which led to their death. The next thing I looked at was also comorbidities. What are those comorbidities that were associated with the cause of death for these patients? So we have hypertension, cardiovascular disease, and diabetes. So you can see the spread of the various comorbidities across the 2 different cause of death. More patients who died as a result of cancer had hypertension, while fewer had cardiovascular disease and diabetes as a comorbidity. Same thing for patients who died as a result of complications from cancer. So what are the outcomes of these various treatment types? So we had various treatment types. Some patients recovered, some are still undergoing treatment, while some died during the process. So the various treatment types are radiation, surgery, chemotherapy, and immunotherapy. So for patients that are undergoing radiation, let's see how many of them are recovering, how many of them are still undergoing treatment, or how many have died. So you can see that for the various treatment type across, there's actually no significance, nothing of significance that can tell us and say, okay, we have a whole lot of patients that are recovering, those that are undergoing surgery are recovering more, or those that are undergoing chemotherapy are recovering more. Because if you look at this visualization, you can see that it is an equal spread across the various treatment type. Next, I decided to create a time data column. And what is a time data column? Time data are differences between 2 date values. So for example, what's the difference between today and the last 2 days? Is 2 days, right? So we want to get what is the time difference, what is the time spacing between when a patient was diagnosed of having cancer and when the patient started treatment. So we want to get the time data, and the most easy way to do that is to subtract date. So you can see one very importance of where we had to do that date conversion, which we did earlier when we converted the treatment start date column and the diagnosis date column to date data type. If these were still in strings or objects, you will not be able to subtract it, right? Because you can't subtract a string from another string. So you have to convert it to a date data type, and with dates you can carry out subtraction. So we'll be subtracting our diagnosis date, which is the date that patient was diagnosed of having cancer, and we'll be subtracting it from the date the patient started treatment. So we want to see this time difference. So with that, we were able to create another column, and we call that our time data column. So you can see we have 4 days, 26 days, 171 days for the different patients. Now what I want to do next is to create a categorical column with these values, and we're going to be creating labels for these categorical columns. I'll be classifying it as immediate start, early start, moderate delay, and delayed start. So because we want to analyze if this had to do with the outcome of a patient, is it that people started early recovered on time, or did they make recovery, or people who started late died, or does it really not matter? So this is what we want to get. So to do this, we use the same process which we did earlier when we try to create our categorical age column. So we created our bins using the mean value, our 25th quantile, our median value, the 75% quantile, and our maximum value, and we saved these as our bin names. With this, we'll be passing it inside a list, and also our labels. Remember I said that labels will be immediate starts, early starts, moderate delay, and delayed start. So for immediate starts are people who started from 0 days. So the day they found out that they had cancer, they started their treatment. So from 0 up until 44 days as immediate starts. Why? Early start is from 45 days up until 90 days. Moderate delay is from 91 days to 135 days, while delayed start is from 136 days to 179 days. So with this, we're able to create our categorical column calling on the pd.cut method. The pd.cut method is going to take in the column which you want to cut. That's the column you want to categorize, your label values, and your bins. So if I run this code, we would be getting our time data underscore categorical column. So we could see our time data column, which is the difference between the date a patient was diagnosed and the date a patient started treatment. So for this person, it took 4 days to commence treatment, and we can see under the time data categorical column is categorized as an immediate start. Okay, so the next patient took 26 days to commence treatment, and you can see we have an immediate start also, while the third patient took 171 days to commence treatment, and it is labeled as a delayed start. So let's go down. The next thing I did here was to create a Gantt plot to see if these various outcomes were determined, or if the time it took for a patient to start treatment, does it influence the outcome of the treatment of a patient. And with this, you can see that there's actually really no significant change in these values. They are almost all on the same scale. Okay, so we cannot really say that the time it takes for a patient to start treatment affects the outcome of that patient. I ended this by looking at the various hospital and the treatment outcomes. So we want to see, is it that in a particular hospital patients are recovering more, or in a particular hospital patients are dying? So we want to know those answers. We can see for the Cleveland Clinic, Abu Dhabi, we have more recovered patients, but if you look at across other outcomes, they are technically also on the same level. Okay, so that is the end of this data analysis, and I could have ended this as writing our key insight. So I would actually leave you to do this. Always remember that at the end of each project analysis, write out those findings you've gotten from your data set. Communicate your findings and insights. Okay, so this brings us to the end of analyzing this project. I hope I didn't take too much of your time, and I hope you enjoyed the process. So if you did, ensure to subscribe to my YouTube channel and also leave a thumbs up. Also drop your comments and questions. I know you have a whole lot of questions you want to ask me, right? So drop those questions and drop your comments in the comment section. Also make suggestion on what you would love to see in this YouTube channel, and please endeavor to share to your friends, your families, and your loved ones you know are interested in analyzing healthcare data. In this space, we talk about data, healthcare, and everything in between. Bye for now, and see you in my next video.